What if helicopters didn't need traditional propellers at all? Engineers are now adapting a nearly century-old maritime invention, the cycloidal rotor, for flight. Unlike normal helicopter blades, this spinning drum design is quieter, easier to control, and way less complicated. And it's not just theory. Real prototypes are already flying. This breakthrough could solve some of aviation's biggest challenges and completely reshape how helicopters are designed and used. Helicopters are life-saving machines in emergencies, yet after nearly a century of innovation, they still play almost no role in everyday urban transportation. That disconnect points to deeper issues, ones that go beyond what most people assume. Start with the numbers. Traditional helicopters require intensive maintenance roughly every 25 flight hours. In contrast, commercial airplanes can go more than 100 hours between major service intervals. That gap adds a hidden cost, making helicopters too expensive for everyday city travel. Then there's the noise. A typical helicopter produces 85 to 90 decibels from 500 feet above, about as loud as a garbage disposal or heavy traffic. But it's not just volume that's the problem. It's the signature. The rhythmic blade slap cuts through ambient sound and travels farther than noise from most other aircraft. Cities like Los Angeles and New York have logged hundreds of resident complaints per month, tied directly to helicopter noise. The disruption isn't subtle, and it's one of the main reasons communities push back so hard against expanded use. The design itself makes things even more complicated. A single rotor helicopter can have over 10,000 moving parts, each one needing precise calibration and regular maintenance to avoid failure. The main rotor head alone contains dozens of joints, bearings, and linkages, all under extreme stress. That level of complexity doesn't just drive up costs, it adds countless ways things can go wrong. One part shows the risk perfectly, the swash plate. It lets the rotor blades change angle mid-flight, which is critical for lift and control. But if it fails, the pilot loses both. It's a single mechanism that makes flight possible and can also cause total disaster. Urban environments only make this worse. Despite their high-tech image, helicopters have trouble moving sideways and rely on forward motion to stay stable. They create powerful downwash near tall buildings, making landing zones dangerous and requiring big safety margins. That makes precise flying in crowded cities extremely difficult. All of these factors push operational costs for proposed air taxi services above $50,000 per flight hour. At that level, the economics only make sense for emergency missions or elite transport, not everyday commuting. And these aren't minor hurdles that software updates or smarter parts can fix. The noise, the fragility, the sky-high costs, they're baked into the basic architecture, which hasn't fundamentally changed since the 1940s. In many ways, traditional helicopters have reached a design dead end when it comes to scaling in cities. Solving this requires more than refinement. It means abandoning legacy rotor systems altogether and building something new, something that solves these problems by design, not by workaround. And as it turns out, a promising alternative has been quietly flying in a very different context for nearly 100 years. In 1930s Austria, engineer Ernst Schneider tackled a problem that had frustrated ship captains for generations. Large vessels needed to navigate tight harbors with pinpoint accuracy, but traditional propellers only moved them forward or backward. Docking became an awkward, risky maneuver, especially in crowded ports where missteps could mean real damage. It wasn't just a maritime issue. Conventional propellers, both in ships and aircraft, share the same core limitation. They only push in one direction. Shifting that thrust requires clunky mechanical systems and compromises control. Schneider saw the flaw not as a minor inefficiency, but a dead end. To fix it, he realized he'd have to rethink propulsion from the ground up. And that's exactly what he did. Instead of relying on one large spinning blade, he designed a system of vertical blades that rotated around a central hub. But here's the key. Each blade could independently change its angle as it moved. Thousands of times per minute, these blades would adjust to redirect thrust instantly, in any direction. This wasn't theoretical. It worked. The system, now known as the Voith-Schneider propeller, or VSP, gave ships complete control over their movement. Sideways, diagonal, pivoting in place, it could do what no traditional propeller could manage. Tugboats equipped with VSPs became surgical instruments in the water, sliding laterally, spinning on spot, and holding position even in high winds or strong currents. If that sounds like science fiction, harbor pilots today make it look routine. Using VSP equipment vessels, they can guide massive cargo ships into position with centimeter-level precision, applying force exactly where it's needed. This isn't experimental tech. It's in use around the world on ferries, offshore rigs, and port tugs, quietly powering some of the most demanding maritime environments. But here's where it gets even more interesting. Aviation actually had the idea first. Back in 1909, Russian aviation theorist Nikolai Yegorovich Zhukovsky proposed a flying machine using rotating airfoils, what we now call cycloidal propulsion. The concept was promising, but early attempts failed. Materials were too fragile, control systems weren't sophisticated enough. And so the idea was shelved, only to find its footing decades later, in ships rather than planes. Yet the core physics never changed. Water and air may differ in density, but both obey the same laws of fluid dynamics. The precise instant control that makes cycloidal propulsion work at sea should, in theory, work just as well in the air. And after nearly a century of proven success in some of the toughest marine conditions, the technology's reliability is no longer in question. What held it back from flight wasn't physics, it was the tools of the time. Now, the advanced materials and modern computer systems, the real question facing aerospace engineers isn't if this kind of propulsion could work in the sky. It's why not now? In today's most advanced cycloidal propulsion systems, each blade acts like an independent engine, adjusting its thrust direction over 1,000 times per second. This stands in stark contrast to traditional helicopters, which rely on mechanical linkages and swash plates, systems that introduce delays and restrict agility. Cycloidal designs bypass those limitations entirely, giving each blade full control authority in real time. The real engineering hurdle lies in synchronizing all those blades while keeping the aircraft stable. Each one has to respond to flight control commands within milliseconds, constantly adjusting based on the position and angle of every other blade. Decades ago, this kind of coordination was simply impossible. Now, thanks to modern servo motors, it's not only possible, it's precise. These small motors make constant micro-adjustments, guided by sensors and flight computers. As the system tracks changing forces, pilot input, and balance, each blade adjusts its angle on its own, in real time. What used to be mechanically impossible is now fully programmable.